International Conference on Sustainable Engineering and Materials Development, ICSEMD 2021. As a participant of the 2021 International Conference on Sustainable Engineering and Materials Development, you are now part of a community poised towards contributing to a better tomorrow. This community consists of scientists, engineers, members of academic and research institutions, students, industry players across the globe, and organizers of this event that will be interacting on a 3-day virtual conference on sustainable engineering and materials development. Renowned professionals that will be gracing the occasion are ICSEMD 2021 is an incredible platform to network with top professionals in sustainable engineering and materials development. In preparation for this event, thorough peer review was done by the Technical Review Committee, and good decisions were arrived at accepting top papers based on scientific content and structure. In that regard, the organizing committee advises that you proceed with your registration and prepare for the conference held September 22 to 24, 2021. Kindly proceed to register for the conference and make your payment by creating an account or logging into your account on www.labingate.com. Click on the ICSEMD payment from your profile and generate an invoice. Further communications about the conference will be made available to all participants. Many thanks to ICSEMD 2021 partners, Labingate Incorporated, Canada, and Bells University of Technology, Nigeria, and exhibitors, CERC Malaysia, Centralized Analytical Laboratory, CAL, University Teknologi Petronas Malaysia, Planet 3R. We are looking forward to seeing you at the conference. Watch out for ICSEMD 2022.
Thank you. Thank you, Dr. Desmond. I would now like to introduce the keynote speaker for the ICSEMD, Dr. Marwan Hassan. And first, I'd like to just go through a brief biography. Dr. Hassan is a professor of mechanical engineering at the University of Guelph in Canada. Dr. Hassan received his Bachelor's of Science degrees in mechanical engineering from Helwan University in Egypt in 1990. His master's was from Tuskegee University in USA, and he got that in 1995. And his PhD degree is in mechanical engineering from McMaster University in the year 2000. He also worked as a professor in mechanical engineering at the University of New Brunswick, Canada. He developed and taught several graduate courses covering flow-induced vibrations, nonlinear finite element analysis, and advanced dynamics and noise. Professor Hassan is a member of several prestigious societies, such as the Canadian Society for Mechanical Engineers, the Canadian Nuclear Society, and the American Society for Mechanical Engineers. He has over 20 years of experience in the area of flow-induced vibrations and finite element analysis. He was involved in investigating several nuclear power plants in Canada and around the world, and worked with nuclear industrial partners such as the Canadian Nuclear Safety Commission, the Atomic Energy Canada Ltd, and Ontario Power Generation. Examples of his involvement with the nuclear industries include investigating the reliability of the steam generators of the Bruce Nuclear Power Station, modeling of the tube bundles in the steam generators of the Darlington nuclear power plants, and the fuel bundle assessments of the CANDU reactors. Dr. Hassan has been a member and chair of the International Fluid Structure Interaction and Nuclear Power Plant Scientific Committee. Dr. Hassan has published over 100 research papers in prestigious journals and symposia, and trained over 50 engineers in the area of nuclear power plant component design. In 2012, Dr. Hassan received the American Society for Mechanical Engineers Editor's Choice Award for Outstanding Paper for Pressure Vessel Technology. This award is only offered once a year for outstanding technical research that contributes to the design, analysis, and development of pressure vessel components and their applications in nuclear power plants. Without further ado, I'd like to hand over the floor to Dr. Marwan Hassan, who will be presenting a speech on integrating sustainability in engineering prediction and reduction vibration-related degradation and structures in the Canadian nuclear energy sector. Thank you, Dr. Marwan, for joining us today.
Thank you very much, Safa, for this nice introduction. And so can you hear me?
Yes.
Okay, very good. Thank you very much. First of all, good morning or good afternoon or good evening. I've seen there's a lot of people from different parts of the world. So again, depending on your time zone. So again, good morning, good afternoon, and good evening. So I'm going to share here my screen. And okay, so I was trying to figure out what would be a topic, okay, and what will be the title. So it's kind of like was torn a little bit between a few different ideas, but I think finally I choose that one. So safe and efficient nuclear industry, the bridge to future energy plan. So, all right. So if you wonder where Canada is, so here is Canada. So this is in the what's that? And so Canada here is in the northern part of the North America. So it's a huge country. So I'm gonna go a little bit. So this is where I live and work. So this is a province of Ontario. It's kind of the middle of the continent. And I am really going down here into this part of Ontario. So this is southern Ontario. Okay, here it is. And here is Guelph. This is where I work and live. Around us, so major cities are Toronto and Hamilton. Now, so I'm gonna start with this alarming slide. So, okay, code red for humanity. All right. If you have been following the news, less than 2 months ago, the IPCC, so this is the Intergovernmental Panel on Climate Change, have issued their latest report. And it was really alarming. And the UN chief called it code red for humanity. Okay, so what is in the report? I'm going to summarize it in these 4 bullets. Okay, this decade, the temperature has risen 1.9, or the temperature has been higher, 1.9 degrees higher than between 1850 to 1900. So within this 100 years, maybe, yeah, a little bit over 100 years, so we got 1.9 degree higher. In the past 5 years, it has been the hottest on record. Okay, we all have seen it, and there's a lot of forest fires and so forth. So I mean, like it's kind of like you can see it. Okay, the rate of sea level rise has nearly tripled compared with the beginning of the century up to 1971. So there's a global retreat of glacier and decrease in Arctic sea ice. So in order to avoid this disaster, okay, temperature rise must be kept below 2 degrees this century, preferably 1.5 degrees. All right. So 2 degrees were really at the edge. Okay, 1.5, we might actually do it. All right. Now, okay, so any temperature rise should not be more than 1.5 degrees to 2 degrees, okay? But can we do it? Can temperature rise be kept below 1.5 degrees? All right. Let's look a little bit at the history, okay? So we are, as human, with our activities and the development of the industry and our usage of energy, we have emitted 2,400 billion tons of CO2. All right. To us, if we added 500 billion tons of CO2 more, all right, we will have a 50-50 chance of staying under 1.5 degrees. Okay. This is the goal, remember, 1.5 degrees. All right. That can only be attained if we kept our emission under 500 billion tons. We have a 50-50 chance. All right. So what is our emission right now? It's about 40 billion tons. Okay, you see that this is not, that seems to be, if we're going that way without deep cuts, all right, and maybe in 10, 15 years, we're gonna arrive at the level where we're gonna be, reaching the 1.5 degree. Okay, so the 1.5 degree will be reached by 2040 in all scenarios. Now, if emissions are not slashed in the next few years, okay, this will happen. Again, this is not what I'm saying. This is the IPCC. All right. So code red is very fitting. So we have a problem. We have a major problem. Now, the IPCC, one of the ways, I mean, this is one of the ways. I'm not saying, okay, there is a lot of things that we can do, all right, to reach our goal. So I am going to focus here in the part of energy. So in the energy part, okay, we can go into electric cars, and we can do other things and recycles and so forth. But I'm talking about here about energy, which is basically major contributor to the greenhouse emissions. So achieving deep cuts in emission will require more intensive use of greenhouse gas technologies, low greenhouse gas technologies, such as renewable energy and nuclear energy and so forth. So low greenhouse gas type of energy like wind, solar, hydro, nuclear, and other. Which to choose? All right. I'm not going to tell you which one to choose, but at the end, you will see where I'm going to lean to. You're going to see that I'm not saying that, okay, we should choose nuclear, okay? All right. I'm going to make a case that all of these should be included, okay? And we're going to see in this presentation here. So, okay, so I'm going to go one by one. So nuclear, it's actually cheaper compared to fossil, all right? It's high efficiency, basically less to no pollution. Okay, you see here, there is a little bit like white smoke. This is not actually smoke, this is actually vapor. So this is not actually CO2, okay? They are reliable and they lead to economic growth, okay? The cons, sorry, so the one to the right, these are cons, so my mistake, okay? So the cons, they have higher initial investment, and there's a lot of concern about waste management and safety. Solar, they are renewable, all right? So you don't need to use any fuel. They are eco-friendly. But the cons, they are higher initial investment. Okay, they depend on the weather condition. So if you have a cloudy day or a day where not much of a sun, so you will have a problem. Okay, they have a longer return on investment and less efficient compared to fossil fuel. And it is location dependent. So if you are in a nice sunny place, let's say Africa, Asia, all right, Middle East, so that this will work very well, but some northern climate areas where you don't have a lot of sun, it will be an issue, okay? Wind, again, it's renewable, okay? It's eco-friendly, okay? There's no emission. The cons, again, it's high initial investment, okay? Weather dependent, so if you have a day that is windy, so that's fine. You have some other days which is, you don't have wind, so you have an issue, okay? Noise and visual pollution, okay? They are a little bit noisy. And people like wind, but you don't like them in your city, okay? So you don't want to look at them, all right, around your building. Like here, this picture here, this is in the city of Amsterdam. So visually, they are not that pleasing. Okay, and there's some issue with local wildlife. Okay. But also one of the problem is the transmission infrastructure. All right, so if we look at the average capacity factor, which is the availability of power, okay, so we see here nuclear is around 93%. What does it mean? It means the nuclear power plant will produce its rated capacity 93% of the time. Okay, where if we go at the lower end of the spectrum with solar, it's around 25%. 25% of the time will give you power or will give you their rated power. So there is an issue here with respect to availability. Okay, some of them will not be available all the time. So issue again, it's intermittent source of energy. In case of wind, if you have wind, it's good. If you don't have wind, you have an issue. In case of solar, solar basically the same thing. If you have sun, okay, you will have good source of energy. If you don't, okay, you have to figure out what to do with that. Okay, like in fact, if you really rely in only solar and wind, okay, or only one of them, all right, every solar plant, it has to have a nearby a gas operating power plant, such that when you have no energy produced, okay, you fire up the gas power plant to actually chip in. And the same thing for wind. So they really can't stand on their own. All right, so that doesn't mean that we should not use them. Actually, we should rely on them, and the future basically will depend on them. I'm just saying that what we have right now. So, and this will require basically development of energy storage and so forth. So we have to work on that. We have no choice. Transmission, there is an issue because often these installations are far from consumer, all right? And this is not like one plant in one place, but again, you have to actually work in the transmission. So it might need more infrastructure as far as transmission. So, and also they actually occupy larger space. So for example, in case of wind, it's 400 times more space than traditional power plant, which is basically very concentrated. So, all right. So this is to give you an overview about in the last few decades on the development of carbon-free power plants. Okay. So so again, it gives you like how many kilowatt hour per capita in each country. So you see here, Sweden between 1976 and 1986, right? They have very large chunk of power development that is actually, CO2 free. So this is clean energy. But that trend has declined, all right? And now you see in that decade, so China, for example, between 2004 to 2014, produce far less. But again, this is per capita. So you have to think about per capita. China is a big country, all right? So 1.4 billion people. So again, you need a lot to do to be like Sweden, for example, so per capita. But again, United States between 2004 to 2018, again, they developed, new renewable energy sources, but again, is not as much. All of those blue bars here, which is very large, these are all basically nuclear. So when you add nuclear, because nuclear has very high amount of energy, okay, so you're actually adding a lot of capacity, where solar and wind, all right, these are small units and you need to do a lot of them to actually have an impact. Again, I'm not saying that we should use only nuclear, but I'm saying that wind and solar and nuclear, the three of them are very important and we have to do them together, all right? So I'm going to compare here two countries, which is France and Germany, and they have two choices. So both of them started to go with nuclear, and or they have nuclear as big chunk of their energy, strategy. So Germany started to phase out nuclear, and France is committed, 100% committed to nuclear. So France, as you see here, is 91% have clean energy, and I think 85 or 87%, I have to check the latest number, 87% basically nuclear. And you see overall, France has 91% clean energy, Germany has 48%. And again, that has a price. Okay, so you see France is paying far less per kilowatt as far as electricity. I'm talking about consumer. So Germany has a goal to increase its solar capacity by 50% by 2030. Okay, and this will only add to their capacity by 9%. So although it's 50%, but in the overall capacity, it's 9%. And you have to remember, again, Germany has a lot of coals and a lot of gas, and they are using. So this is like dirty sources of energy. So how much electricity cost? So Denmark is basically the highest, as 40 cents per kilowatt hour. All right, and you get at the other end of the spectrum is India is 8, China is 8, Canada and United States is around 10 to 11. All right, now Denmark is very high again, but Denmark relies a lot on wind energy. All right, and that is, if you rely on wind energy alone, it's very expensive. Okay, someone said, well, it's basically, it's a cheap source of energy. Yes, but again, you have to have backup power plants. Okay, and that's what drives the cost high. If you have only wind, and the wind is a source and it is 100% working all the time, that number will have been very low. Okay, it would have been very cheap. But what makes it high is, yes, it is the initial cost, and you have to have the backup power plants. All right, let's get into Canada. So Canada, as I say, it's a large country. It's a federal country, so it has provinces, and it depends on the province that you are in. So some provinces to the left, like Manitoba, Quebec, Newfoundland, Yukon, British Columbia, they rely, or they actually produce a lot of their energy from hydroelectric. Okay, so for example, Manitoba, 97% of their electricity comes from hydroelectric. All right. And the other end of the spectrum, you have Alberta, Saskatchewan, Nova Scotia. They rely more in coal and gas. So Alberta, 84% of their energy coming from coal and gas. All right. Now, this is not fair comparison, because in some places they don't have a lot of hydropower resources, so rivers and so forth. And okay, so Manitoba has a lot of rivers, Quebec has a lot of rivers, and that actually allows them to produce a lot of energy from hydroelectric source. So again, so the comparison here is not very fair, but that shows you the diversity in Canada as far as power. Now, I'm gonna focus on the example of Ontario. So Ontario, this is where I live, all right? 92% of the energy comes from clean sources. This is a map of Southern Ontario, and it shows you here the location of the plants. We have here two gas-fired stations, so one here and one here, and we have 3 nuclear power plants. We have Darlington, Pickering, and Bruce. So these are the 3 power plants. And we have lots of hydroelectric power plants all over here. We have wind, one here and one here, and there's some others too, but these are the major ones. And also we have a solar, again, this is a major solar power plant. But again, you have a lot of smaller ones scattered all over. So this is a great mix of energy. And if you look at here, the proportion, again, this is basically average. So nuclear constitutes 60% of our energy here in Ontario. 25%, a little bit more or less, is is hydro, 7% wind, 6% gas, and solar is 1%, and biofuel is 1%. It's a great mix. You have 92% of the energy coming from clean. Now, this graph here shows the greenhouse gas emission forecast. Okay, Ontario is very aggressive in adopting clean energy, mainly nuclear, and they started in 1976. They were adding 16 nuclear reactors, and they start to phase out the coal power plant, and we actually achieved great cuts in our emission. We reached to 90% cuts by this time here by 2015. Unfortunately, the forecast for the future is not great. Okay, it looks like we're gonna triple our emission in the last 20 years. All right, so we start to see a reversal in the trend. Okay, and we're gonna have more greenhouse being produced, actually triple what we have. So we are losing what we have achieved in the last 30 years. Okay, the problem is basically we're going to see the problem. So the problem is we are not adding more of renewable. We are having a lot of energy added by nuclear, and I'm going to go here. So this is one of the okay, so this is a snapshot in one of the days, and this is actually you can actually go to the called energy grid. An energy grid will give you live update on how much energy from what sources, and you can see that in a one day. So you have 51% in nuclear, hydro 20, wind 17.8%. So this is a good day for wind. All right, a nice day. So you get some wind. Gas 9.2, solar is 0.8, biofuel is 0.2, and then you get in a second day. All right, you don't have a lot of wind. All right, 1.1, but the nuclear can chip in and basically substitute for how much is being lost because there's no wind. All right, that day was very low day for solar, but again, you can have this system where basically nuclear will give you the base load, and if the wind goes down, all right, when nuclear can basically chip in, and hydro too. So I think that's a great mix, and it shows you here, well, this is a system where you can have renewable energy. They basically complement each other along with a clean energy such as nuclear. All right, it's a good picture, but we want more. We would like to have wind and solar to play more role, okay, and to give us more energy. But again, just going to be so actually this is this morning. This is actually before I looked into this. I was checking like how much energy do we have. So nuclear this morning. So this is around 8 o'clock in the morning. It was 64% nuclear, hydro 20%. Wind is 13.7%, so that's good. Solar is still just early in the morning. The sun is not out yet, so maybe by the midday we're gonna have more energy from the sun. So what I'm saying here, combination of nuclear, solar, and wind will be the future. Will be our way out of this code red. Okay, and I showed you example of the province of Ontario and how this working. All right, but also need rapid development of storage capacity. All right, storage capacity especially for wind and solar. Okay, so that we can rely less on gas and other sources. And to enhance the safety and reliability, I'm going to talk about this because I haven't talked about the elephant in the room, which is nuclear. Okay, nuclear has its own problem. All right. So what are the problems with nuclear? So the problems are environmental. economical, and safety. Every time you hear nuclear, okay, people just start to get worried about nuclear, okay, because in their mind, okay, nuclear means, okay, nuclear bomb and Hiroshima, Nagasaki, and so forth, and okay. So it's actually safety, economical, and environmental. And again, one of the environmental issues. So you hear about Chernobyl. So this is a disaster. Fukushima, that's a disaster. Again, these are issues and they exist, and these incidents, they actually existed. But we have to put things into context. So Chernobyl, this power plant would not have been licensed anywhere in the world because it was not safe. Okay, so it didn't have containment. The concrete containment was not there. Okay, all of the new power plants, they have concrete containments. Okay, and they are quite safe. But it was a concern. Fukushima was another incident. It's a major incident again. But you know, people look and hear about Fukushima in Japan and say, okay, there's so many deaths. In fact, all of these deaths, they came from the tsunami. It didn't come from the nuclear power plant accident. In fact, there was 0 death came from the accident at Fukushima or from radiation. That's what happened. But again, because it happened where the tsunami took place, okay, people are mixing these two together. All right. Economical, nuclear is perceived to be very, very expensive. Okay. In fact, if you look at the nuclear and you look at the levelized cost of energy or cost of electricity, you can go to the internet and you can look at it, which basically it's factors that looks at the initial cost, the running cost, the cost of fuel, and so forth. You find nuclear, it is okay. Okay, it's not the cheapest, but it is okay. All right. So, and again, most of the cost that comes initially, it comes if you look at the total cost of the of making or producing or building a power plant, around 20% of the cost. This is actually the cost of the nuclear reactor, this nuclear steam generator, and all these beautiful machinery, all these beautiful devices, and the electronics and everything. 25%. So where is the 75% is coming from? Coming from excavation, like digging and moving sand and concrete, and okay, and acquiring material, and also the cost of the regulation. The regulators sometimes change their plans halfway through the building, and you have to alter the design, and that costs a lot of money. Okay. France is a great example that had the regulator, the manufacturer, and the operator, they all work together, and they have one design and they go with it. They don't change it, and they keep the cost down. Where in the United States and Canada, so there is an issue with the regulator where basically changes the design halfway, and that will increase the cost. Okay. Safety. Safety is an issue. Again, you're talking about leakage of radioactive material and so forth. But again, throughout the history of the nuclear is very safe. All right. And I have this example here. So this is an Airbus, and it's a big, huge aeroplane. And the last time I was in one, I think it was 18 months ago. This is before the pandemic. It was in February, and I was flying to Marseille, France, and I was giving a lecture about nuclear fuel bundles and so forth. So this was the last time I actually was able to ride a plane, and hopefully, in the future, the pandemic will ease and we'll be able to travel freely. So it's a big plane, okay, 2 engines and stuff like that. This is a joke, by the way. So what if this plane is being built by nuclear engineering. It's going to look like this. All right. So it's going to have more engines. It will have, more, landing gears and so forth. So nuclear power plant manufacturer and operator, they actually contain a lot of ways of safety and redundancy in the system. So throughout my work and my group, we have been working with a lot of industry and a lot of partners here, and a lot of this work related to the reliability and safety of nuclear power plants. So this is what I'm trying to say here. Okay, nuclear will be the future, all right, and will be the future combined with the wind and solar, all right, and together we'll be able to achieve, we'll be hoping to be able to achieve our goal. So, okay, but this is the first part. So I'm going to talk about the second part about one issue of nuclear, which is safety. And I'm going to pick up one topic here, and we're going to show you how we deal with it, how we model it, and how we enhance our knowledge in that area. So, so shell and tube heat exchanger, this is one major part of nuclear power plant. It's not only nuclear power plant, you can find it in process plant, pulp and paper, and so forth. And it's basically bundles of tubes. So tubes that are bundled together. So in that shape here, in that shape here, this actually can do full bundle. So, and they are heavily used because they can give us larger ratio of heat transfer due to volume and weight. And they are basically easy to construct, okay, in wide ranges of sizes and shapes. And so bundles of tubes, again, you put them in larger cylindrical shells, and you put baffles here to prevent them from moving. But you also can have gaps and clearances here at the support to allow for assembly and to allow for thermal expansions. Tubes can be arranged in many patterns, so like normal triangular array, parallel triangular array, square, rotated square, and the pitch here is the distance from center to center. All right. The triangular layout, it gives more tubes in a given shell. Square array makes the cleaning of the lanes to be much easier. Okay, so this is the layout of a nuclear power plant. Okay, so you have here, this is the reactor. All right, this is where the nuclear reaction takes place, and again, you get very hot liquid under very high pressure, passes through here into the nuclear steam generator. Okay, where heat transfer takes place. You put fresh water, the water extract heat is converted into steam. You separate the steam into turbine here, and you produce energy. So there is no firing. Okay, there is no production of CO2. Fairly nice and clean, and so forth. And you can cool down or condensate the vapor again, and you can pump it back into here. So it's a closed circuit. So now the older design were basically robust, basically over designed, and vibration problem did not exist. All right. Now, new design, they are highly efficient. So we start to use thinner component, and we start to try to push the system to produce more electricity. So we have higher flow rate. That created vibration problems. And especially here in the nuclear steam generator, which is, I showed earlier, which is very large structure. You have tubes in the shape of U-bend, and they are long, they are flexible. And the picture down here, it shows you how they basically assemble this U-bend tube. They take it tube by tube, and they push it in. And this big stuff here with holes, this is where they have to fit in. These are the supports, all right? And we have clearance because you would like to push it in, you would like to set it inside. So it's a very complicated process. And this one it's around between 15 to 30 meter high. It's a very big structure. So, but the clearance is once it exists, it will allow the tubes to vibrate and impact and contact with the support and can cause fretting wear. So now, because we have an external fluid flow, you get a coupling, okay, and the coupling controls or basically exchange of energy between the fluid and the structure. Okay, the structure response can be stable, like in this case here. This is a vibration, and this is versus time, and you can get a little bit of perturbation, but the system will be able to absorb this and it damps out. Or it could be unstable, so you can have initial disturbance, and actually disturbance grows, and you will have a problem, because if it grows that much, it will cause very high stress and it will cause failure to the tube. Failure in tubes in power plant, it's a problem because these tubes contain most of the time radioactive material, and if it leaks to the fresh water, we'll have a problem. All right. So the types of vibrations that we can have is forced vibration, like turbulence. We have self-controlled mechanism as a like vortex shedding. This is like typical vortex shedding problem, or acoustic resonance. Or you have self-excited mechanism, like galloping and fluid elastic instability. So galloping or flutter. If you are a person who study aeroelastic and aeroplane wings, flutter is very common problem. If you are a person in studying machining operation, they call it the chatter. The same exact phenomena, all right, which is feedback control between the force and between the response of the structure. So what would happen if we don't deal with it? Well, you can have some issues. So these are some of the examples. So this is here, after only 10,000 hours, you have wear marks here in some of the tubes, and after 13,000 hours, you have a leak. Okay, just to give you an example, these structures should last with minimum maintenance for something like 30 to 40 years. So this is 1,000 hours. This is very short period. And here is an example also. One of the steam generator here is only after 13 days you start to have breakage, and you start to have also leakage. So leakage is not good. This is what we're talking about. Now, to look at turbulence excitation, how can you predict the response of the structure? All right, we often use the power spectral density of the turbulence excitation. And we can use this simple equation here to predict what will be the response. All right. Turbulence is not going to cause the tubes or the nuclear steam generator to fail suddenly. It's a long-term mechanism. It could take years and years and years, and you can actually notice it before it actually breaks. So it takes a very long time. So this is a long-term excitation mechanism, and we can easily design against it to have a safe operation. The one that's actually a problem is called fluid elastic instability. This is the one that we have to worry about a lot. All right. And here is basically the response, and here is the flow velocity. So if you increase the flow, so you want more energy, so you increase the flow, and as you increase the flow, the response increases. And then, I mean, this is nice and gradual, but then at a certain point, it's actually you have a very large increase in the response due to a small increment in the flow velocity. And this is what we worry about. We call this the critical flow velocity. We don't wanna operate anywhere near here. We would like to operate somewhere here. And that's why knowing this is very important. So here is a tube, here is a flow. This is a streamwise direction. This is the transverse direction. This is a support here. So we have a support. You have a gap. And
yeah, it's sustainability and materials engineering conference.
Okay.
Color me confused.
Yeah, is on.
Okay, if you please, could you mute your microphone? Okay, so anyway, so most of the times, actually, not most of the time, I mean, we all for the last 40 years perceive this mechanism to work only in the transverse direction. So the problem only arises in the vibration of the transverse direction. The streamwise direction was not considered to be a problem. So it's always in the transverse direction. In the recent year, that turned out to be not true. All right. So it's transverse, but it could happen also in the streamwise direction. The design approach here that we must avoid this mechanism. This is a critical flow velocity. This is something called mass damping parameter. It's a parameter that contains the mass of the tube, the damping, the density of the fluid, and the diameter of the tube. And here, let's say that if you are here at mass damping parameter of 10, so you should actually, this is a limit. This is a critical flow velocity. If you want to operate, you should operate here. You don't want to operate here. These are the experimental data that has been collected in the last 40 years. And this is a line. This is a straight line. We call it the Connors equation, which gives us what will be the critical flow velocity for this given condition. It's been widely used by the industry. How do we simulate this type of structure? So, all right. So one of the issues that we do, or one of the techniques that we do, we use dynamic simulation packages. Okay, and we have developed our own. If you try to do that with commercial packages, it's not going to work. They can't. They don't have the algorithm to deal with fluid structure interaction. You need to have algorithm that deals with the fluid loading. So I'm going to show you here an example. So this is actually a U-bend. This is one tube within a nuclear steam generator. This is a flow distribution, mostly two-phase flow. And we take this system and run it into a time domain simulation. And I'm going to talk about this. And you can be able to predict stresses. And from the stresses, you can predict what will be the fatigue. And you can also predict if there's a crack, how big the crack will be, and what is the life of the component. This will give you the life of the component. And this picture here, this figure here, give you, okay, the propagation of the crack or the percentage of the wall rust loss. So you have fitting wear here and you have a loss in the wall, and how much is that after a certain time. So you can predict the life of the equipment. You can also get the response and impact force, and you can get the normal work rate. And again, we'll give you, with the prediction of wear coefficient, you can predict the fitting wear. All right, and this is here picture here of the vibration of the tube. Of course, this vibration comes with impact and friction and so forth. So the time domain simulation will give you all this information, and you can predict what will be the life of the equipment. And if there is an issue, you will be able to maybe shut down the plant and make some repairs or replace tubes. And this will contribute to the safety of the equipment. So modeling element, in order to do that, you need to model the fluid excitation. So in terms of turbulence, fluid elastic instability, you have to have a structural modeling, commonly used finite element analysis. You have to model the tube, you have to model the loose support, you have to predict fitting wear, and you have to predict tube cracking and leakage. I'm not going to go through the math. So this is our typical beam equation. And you have here the inertia part, the damping part, and the stiffness part. And these are the external excitation. This is fluid elastic forces, turbulence forces, impact forces. I'm going to go quickly over these elements. You do spatial discretization using finite element. So you convert it from a continuous form into a discrete form. And then you do modal discretization, which is another level where you reduce the order of the equation. Structurally, you use beam element to model the tubes. And so this is here at 6 degrees of freedom, sorry, 12 degrees of freedom beam element. You have 6 translation and 6 rotations. As far as impact between the tubes and the support, we use a so-called single point impact. It was developed by myself and my co-worker. And you look at the support as added stiffness and added damper, okay? And you can calculate the impact force using this equation here. And this is just animation here to show you the tube motion and how it impacts the support. This is very crucial. You need to do that, and you can see that there is also some sliding of the tube and with some friction, which will lead to the so-called fretting wear damage. All right, let me go next. All right, using this technique, you can model any type of support. You can model the rhomboid or flat bar supports. You can model the so-called broach hole supports. You can model circular hole support. If you want to go a little bit much more detailed or much more fancy, you can use a so-called edge and segmental contact. So this is edge contact, this is segmental contact. It's a little bit much more involved. Instead of looking at point, you can look at many points, and this will give you much better information about impact and about friction. This is an example here. It shows you the impact process of the tube with the support, and it shows you how the routine is actually working. Friction model, very important. There are a number of friction models, and I'm going to focus here on the force balance friction model, which is initially introduced by Carnot in 1985, but later we developed this model for nuclear steam generator. And the most important part here, this is here if you use, let's say, the velocity limited friction model. This is like column friction model, and the displacement looks okay, but you look at the velocity and you have a lot of chatter. And this is a problem. You have challenges around the discontinuity around the velocity equal to 0. This is a proper friction model. Okay. Oops, let's go here. This is a proper friction model. Friction model here, you have nice and clean transition from stiction and sliding. You have a sticking, sliding, sticking, sliding, and so forth. And you look at here at the velocity here, you have nice peaks, which basically, so this is sticking, so there is no velocity, and then it's sliding, you have a velocity, and then it's sticking again. Nice, clean signal. This is what you want to see when you are modeling friction. The one to the right is not what you want to see when you model friction. So it's very important because this is going to affect your prediction, okay, and going to affect your accuracy in predicting the life of the component. Okay, so finally, let me see how much time I'm doing. Maybe I have a few minutes. Okay, so I'm gonna talk quickly about how we model flow. We can simplify the flow as basically, so this is a flow inside a tube bundle. We can simplify it as one-dimensional flow, very simple, implicit, incompressible, and we can do that with any type of array. So we can model large number of flow cell, and we have it here. So this is a cell, and this is a flow, and these are the tube, and this is basic cell, and we can repeat this, and we can look at, okay, well, there's an interaction between the flow cell and between the tube. If the tube moves, it pushed against it, you have a deformation in the flow cell, but that deformation doesn't happen instantaneously. There is a time lag, and that time lag what cause instability. Once you have a time phase between a force and a displacement, you have to be worrying because that time lag will cause a velocity feedback, which basically could cause potentially instability. All right, we can use this technique, we can look at U-bend tube, and we can divide it into small little flow cells. And these flow cells, we use finite element to look at the structure, and we use the fluid modeling to look at the flow, and we exchange between these two models, and we can predict instability. So you can predict stuff like that. Again, this is a flow velocity, and this is the response, and you can predict when the instability will take place. All right. And here, this is finally, I'm gonna end up with this here for the interest of time, because I'm hitting 10 o'clock, which is basically the end of the lecture. So you can look at a U-bend steam generator like this, which has many supports, different shapes, like flat bars, like here, project hole supports, and so forth. But each one has different conditions, has different clearances, have different type of flow, have different friction, and so forth. And the combinations are endless. So the best way to do it is probabilistically. So you do Monte Carlo simulation, and between, the randomness at each one of the support, and you take a look at what will be the impact force if we consider all these randomness. And you can take a look at some of the trends here. Thank you very much. And I'll be more than happy to answer your question.
Our first question, Mohammed Abu, do you want to ask your question?
Yes, thank you, Dr. Marwan, Professor Marwan, for this great session and outstanding information and achievement that you clarify for us. I'm actually an architect, but according to the nuclear industry in providing energy and power, could we consider the nuclear power plant as a completely green or friend to the environment facility by considering the waste that these plants are produced that are actually radioactive? Do you have any idea or concept for rehabilitation the waste that also produced in submarines and military and all related to nuclear industry for providing power to be more sustainable and so on? Thank you.
Yeah. Thank you very much. This is actually a great question. This is a very good question. And my take on that, I think the future is wind and solar and other renewable energies. Okay. Nuclear is not renewable. Okay. Why? Because it uses fuel, and that fuel comes from uranium, and we have finite amount of uranium on Earth. It's not gonna renew itself. All right. But wind and solar, you're using wind. So wind comes every day, and solar, the sun, as long as the sun is shining every day, okay, you have energy. So in that sense, nuclear is not renewable. All right. Next, is it clean? Yes, it is clean. All right. Clean in its operation. But the issue with nuclear is, okay, what you're gonna do with the spent fuel? Okay, so, and that's an issue, but my point of view, this is not a technological issue, it's a political issue. All right. The technology exists in how to deal with it. It's going to take longer. So it's not like, okay, you're going to leave it for a couple of hours and you can, after that, you're going to throw it. No, that actually lasts hundreds of years. All right. After the fact. But the new technology, what they do, they actually recycle these waste into new fuel. So you kind of basically cycle it back into fuel. But at the end of the day, even if you recycle a few times, at the end of the day, there is some waste that you have to deal with. which basically they store it on the, so 90% of the fuel is basically stored on the plant. After they use it, they have to last for, I think, like 50 to 100 years, okay, on the plant. And after that, when the radiation goes down, they have to move it away and they have to actually bury it somewhere. So it's not green, it's not entirely green. But what I'm saying is the future is wind and solar. But in order to arrive there, we need a transition to arrive there. And I think nuclear will be the transition to arrive there. In this period for 30 to 40 years, we might need nuclear to cut greenhouse emission, okay? Until wind and solar, all right, become strong enough to give us 100% of the power or 90% of the power, all right? But as it stands right now, it's very hard to make a case that is wind right now is going to give us 100% of our energy, all right? There are issues regarding to storage. There's issues regarding to availability, okay? So this is what I'm trying to say. But what I'm trying to say that eventually it has to be wind and nuclear. Wind and solar. Wind and solar will be the future. This is the future. We have to arrive in the future to be hopefully 100% wind, 100% solar, all right? But in order to arrive there in this transition, we have right now pressing issue. We have to cut emission in the coming, 20, 30 years. How are we going to do that? Okay, how are we going to phase out coal and gas? But your question is correct and your concern is correct. So
thank you.
Nuclear produced waste. Yeah.
Thank you, Professor. Toward that, I have no idea because I'm not involved in nuclear technology. And toward that, do we have any statistics to calculating the range of power plants? You mentioned at the end of cycle, there is a remaining of even very small amount of waste that are radioactive. If globally we are going to making the nuclear technology as a part of providing the energy and power, do we have any statistics to calculating the range of the nuclear power to remaining this waste as much as possible in the limited range? I think.
Yeah. Okay.
Do you get my point?
I will try to answer it. Okay. So I think what you're trying to say that, okay, what we have right now, nuclear power give us 10% of the worldwide energy. It's only 10%. Okay. And it depends on country to country. Okay. For example, in United States, nuclear energy constitute 20% of the energy. Okay, coal in the United States is a big, is around 55%. So 55% of the energy in the United States comes from coal. So it's a big pollution. Okay, and the problem is United States has enough coal for them to continue for over 400 years. You have huge amount of coal. All right. So now, okay, a country in like France, okay, it's 87% nuclear. So they actually made a decision to go nuclear. Okay. Now, what you're saying that do we have enough?
And maybe France, which is 87% nuclear, take the opportunity maybe for the rest of the world or countries. What if the whole Africa or Asia or any other part of the world become 50% nuclear? Do we facing a disaster of nuclear wastes?
Okay, you mean do we have enough resources for that?
no, sir, not resources. The outcome of these power plants, nuclear power plants.
Yeah.
Each nuclear power plant
Yes. Yeah.
have amount of waste.
Waste. Yeah.
If my country, your country, another country, all participant country become a nuclear based impartial nuclear based countries, do we facing a disaster of treating this amount of radioactive waste?
Yeah, we have the technology to deal with it, as I said. So there are stages where you deal with it. So we have the technology does exist with it. So I don't think there is a big problem. There is a disaster. It's not a disaster. Okay, it just basically you have to manage it and you have to deal with it. And the technology does exist. And you know, the whole waste is basically they are, you know, using nuclear energy and you're dealing with it, and there is procedure to deal with it, and you have to learn how to use it. That's basically it.
Thank you for the clarification of that.
Thank you. Our next question is actually from Professor Ajayi, if you'd like to go ahead and ask. Professor Ajayi?
Okay, can you hear me?
Yep.
Oh, okay, fine. Thank you, Professor. Yeah, my question is very simple. The analysis is basically focused on the reliability of the shell and tube heat exchanger with vibration as a condition monitoring. But what about the heat exchanger material? The material, because I believe the material can determine the structural response.
Yeah.
The crack that we initiated,
absolutely,
the propagation of the crack, and eventual fatigue.
Yeah.
What do you say about the material type for the heat exchanger? Or is there a specific material of interest that you're looking at?
Yes.
That's just what I want to know.
That's a very good question. And actually, again, vibrations is a great tool to know the response. But again, at the end of the day, it is the material that will actually either it will withstand this or not. Okay. And for nuclear power plant or nuclear steam generators, the tubes are made of material called Inconel. So Inconel alloy, and it's supposed to be has high resistance to corrosion and wear. All right. So it's very important. And actually, the material could play a very big factor in the survival of the power plant. For example, in the nuclear steam generator, at one point, okay, in the last decade, in one of the power plant, they wanted to produce more. They wanted to produce more energy, but they have a problem with corrosion, so they switched from Inconel 6 to Inconel 7, which has greater resistance to corrosion, but however, it has less heat transfer coefficient, which means it's going to produce less energy. So for them to overcome this, what they have done is, okay, let us pack more tubes, basically, to increase the surface area and to get more energy. And that turned out to be affecting vibrations. It caused larger vibration and actually failed after 11 months. And they had to actually plug some of the tubes and do some remedies. So your question is very valid, because material can basically affect everything, and material is very important. Okay, and if you in the design, you have to consider material and when it's going to fail, because at the end of the day, our analysis, our vibration monitor is to protect the material. So we need to know exactly how is the material is going to behave. Yeah, that's a very good question. Thank you.
Thank you, Dr. Hassan. Our next question is from Olufemi. If you'd like to ask your question now.
Yes, please. Thanks so much, Professor Marwan. Thanks so much for the great talk. So I have two questions, just some form of general question. One is, sorry about the sound underneath.
No, that's okay.
What's your opinion about African countries adopting more of nuclear power generation? of course, you have a root of that from there. So what's your opinion looking at the current state in terms of enlightenment of the people and the resources we have available? So what's your opinion on that? That's one. And then two, can you tell us a little more about, I know you've done a lot of work when it comes to investigation of steam generators and equipment in the nuclear power plants towards development of policies and regulations in the Canadian nuclear industry. So can you tell us a little more about your work in that area? So those are my two questions.
Okay, let's talk first about the first question about let's say the continent of Africa. This is the place where I am originally from, right? Is nuclear suitable for Africa? Okay, I think Africa has a lot of resources. Okay, and we have a lot of sun in Africa, and I think that would be one major area to one major source of energy that we can actually in Africa, the continent, to actually produce. And so solar, wind. I would say the focus would be more in solar and wind, but the continent also should explore nuclear. And the reason why I'm saying that, because if you start to develop energy from nuclear power plant, this will force you to develop knowledge. You develop knowledge in that area, and you develop not knowledge only in the nuclear, but again, in order to produce or in order to make a nuclear power plant, there is a lot of stuff that you need to know. Okay, there's a lot of industry that has to be involved. You have to modernize your manufacturing facilities. You have to modernize your base knowledge in that area. So to me, it is important for the continent to get into this area, to develop their base knowledge, to develop their industry, okay, to learn modern ways of manufacturing and modern ways of analysis. So this will provide with knowledge that will be valuable in other fields. But as far as energy, okay, I think the solar energy will be much more important than nuclear, for the African continent. But again, I think the African continent should also explore nuclear, because again, as I said, that you get into the nuclear, you have to start to develop your knowledge base, and you have to build your knowledge and education and your industry and your manufacturing facilities and so forth. So this will help you in developing your industrial sector. This is for the first question. And for the second question, yes, I did a lot of work and in the nuclear regulation. So I've been working in investigating some of the failures in nuclear power plants in Bruce power plant and in Darlington. And recently we had 2 contracts that we worked on developing some guidance for the replacement of the Bruce power plants, and that was a big project. And in fact, Dr. Olufemi was actually was working with me in that project. So we both worked in that project, and we built experimental facility, and we were doing some experiment to give the regulator some guidance as to what parameters that they can use to have safe operation of nuclear power plants. And lately, we also have been working on the integrity and the vibration of fuel bundles. So this is a nuclear fuel bundles. These are bundles of fuel. So this is actually uranium pellets, included into zirconium tubes, and there are 37 of them, and they are being put together or being placed together with with basically endo plates, and you have hundreds of these, and you put them in the fuel channel, and you have the flow, and you have the nuclear reaction takes place. But you have to keep them cool, so you have heavy water passing through to actually cool it down. But because again of the fluid flow, that's another. You get flow-induced vibrations, and you can get cracking, and you can get issues. And this is another project that we've been working on recently. Thank you.
Thank you, Dr. Hassan. I think this will be the last question from Dr. Desmond. If you'd like to go ahead.
Thank you so much, Prof, for your question. I think that anytime we talk around energy, I think the hydroelectric one is, people are always silent about it. But the idea is that it doesn't produce any green gas effect. However, the challenge there is that because of the low dissolved oxygen levels in the water, so that could affect aquaculture. But then also when you look at nuclear, the idea is that the current energy storage materials that we have, they are not there yet, because now we need to develop a lot of materials. If, for instance, we take Africa, we take the Inga Dam. The Inga, for instance, a drop in an Inga can actually deliver electricity, hydroelectric power to the entire Africa. That is if you take just the Inga one. So what is your take on the fact that we are always silent on hydroelectric power?
Well, I mean, what you're saying is quite correct. All right. Again, hydro, there's a lot of energy resources in hydro, and definitely it needs to be exploited. All right. So I'm not an expert in hydro, so I can't really talk. I mean, obviously you know more about it, but so I'm not sure if there are enough resources, for basically to use only hydro. But I think there is a lot of rivers in Africa, and there's a lot of falls and stuff like that can produce significant amount of power. But in the next 20 to 30 years, you're gonna have population growth, which basically Africa is one of the fastest place in population increase. So in the last 20, 30 years, you could have huge population, and this huge population, they are all getting into, I mean, like Africa now is not Africa 20 years ago. So a lot of places in Africa, they have basically the modern technology, and they have the household technologies, stoves and fridges and stuff like that. So the consumption of energy will be huge in Africa. So will the water, will the hydroelectric will be, I don't know, it might be enough, but I think the energy demand will be huge in Africa, and you have to look at other sources of energy. And it's very interesting to see all this river, but you still in Africa there is a lot of reliance on the gas and coal, power plant, which is cause pollution. However, Africa is not the biggest polluter. Actually, the biggest polluter is basically Asia and the West. All right, and I think the West has to take the responsibility, and basically they have to start to cut their emission seriously. Okay.
Thank you, Dr. Hassan. If you don't mind, we just have one more question. And if any of the participants or professors or doctors have any more questions, if you'd like to provide a contact or somewhere to contact you, that would be awesome. But our last question is from Dr. Kunle.
Thank you. Thank you, Professor Hassan, for the wonderful presentation. I just want to ask this quick question about the impact of additive manufacturing on energy power plants research and development.
Okay. So you know, so energy development, you have, okay, any power plant will have huge amount of parts, okay, and again, it's as earlier question was talking about material, and material is very important. And what we need material that will withstand, you know, the stresses and strains, and will be able to sustain the loads and so forth. And we need also material that will actually sustainable. Okay, so material that we can produce efficiently and will be able to supply this part. So I think additive manufacturing will actually might be playing a role in that, and some of the parts was very hostile, like environmentally hostile, which basically high pressure, high temperature, and stuff like that, might not be suitable for additive manufacturing. Maybe at least the plastic part of it, but additive manufacturing right now, they are, you know, there are new techniques, which is additive subtractive manufacturing, where you can actually deposit layers of metal, and after that you can machine it and so forth. So that might play a role in some of the parts of the nuclear power plant, and especially if these materials will exhibit stuff like corrosion resistance. So corrosion resistance is a major thing in nuclear power plant, and if you can produce some of the parts with additive manufacturing, for example, and such that these parts are corrosive resistant, this would be a big step towards contributing to the energy sector.
Thank you, sir.
No problem. I'm gonna to put my email here and in one, so that I think I can put it in the chat.
Yes, that would be awesome.
Let me see. Chat. I'm just trying to figure out, okay, how to do that. So here is. All right, so I send it to the chat, so feel free to contact me. I'll be more than happy to answer your question, and if you wanna have a Zoom chat sometime, I'll be more than happy to do so.
Thank you so much, Dr. Hassan. We're very grateful to have your time with us and joining the conference. We're all grateful for learning from you. So thank you so much, and thanks for providing your contact information for everyone to contact you.
No problem. It was my pleasure, an honor to come here, and I would like to thank the organizing committee of this conference, and especially Dr. Olufemi for his kind invitation.